In this video, we're going to cover some DcPD testing, how to set it up, and we'll actually run a little bit of a DcPD test. We'll start a crack and we'll grow it some. The first thing I've done during this test is, since I'm just using potential measurement, I do want to have a stable environment to measure the potential in. So I am holding a solution temperature of 150 degrees. I just got to 150 degrees and it is still stabilizing, so this is probably going to come back down what looks like 0.15 tenths of a degree back to 150 and stabilize. That is something to make note of, especially when getting your initial crack length. You can tell I'm still warming up. I've stopped my force hold algorithm and now you can see the force is slightly dropping. Everything is soaking that new temperature of 150 degrees, so you may want to allow some stabilization. But while we wait for that, let's define the test. We'll go to our test profile. We're going to keep our motion selection as creep initially. Using a ASTM standard compact tension specimen with the standard dimensions. We have an initial notch length, not a crack yet. There is no crack in the specimen yet. We're going to pre-crack it in our load frame. So we're going to set the crack length or notch position as 0.4. This is also our initial crack. For instance, if you did have a specimen pre-cracked and you know it's crack outside of the machine, you would enter that known crack length here. We have a W of 1 and a specimen thickness of 0.5 inches. We're going to enable DcPD, and I'm going to set a very small averaging pool. I'm going to keep it a very responsive test, so my average pool sizes are only a pool size of 2. I'm going to make that a little bit bigger. Yeah, I think that should be good. So the nanovolt pool size is how many readings it takes from the nanovolt pool. So you have a forward and a reverse reading twice with this pool size. The initial pool size will be this completed pool averaged and put into this pool. In other words, to complete the initial pool size, it'll take 2 readings of 8 from this pool. Likewise for crack pool size. Here we'll set our current under 10 amps for most of the DcPD systems, unless yours has been made special to support higher current. I typically run 5 amps with good results. Sample rate, since I'm going to run this test for quite a while, we're going to keep it at 30 seconds. That means it's going to take a sample every 30 seconds. I'm going to leave my test duration as 0 so it runs forever or until I stop it or the specimen breaks. I'm going to set my minimum force for 50 pounds and my maximum force to make sure I don't ductily fill the specimen. I'm going to put it 4,000 pounds. The rest of these we can leave blank for now. This has already been defined. Basically, I'm running in solution control and I'm holding 150 degrees Celsius. I have a high pressure limit of 1000 psi. These numbers are automatically defined by entering this 150, yet you can modify them. Post-test cooldown, this means when the test stops, so are the heaters. I'm not going to use any of this right now, but what you could use this for is, say I wanted the test to run in a somewhat automated fashion. For instance, say I wanted the test to start as soon as it reached temperature. I could set If solution temperature is greater than 149.9, I would enter that there, then start the test. So once it hit 150 degrees Celsius, the test would start automatically. And there's 3 of these cases so that you could have 3 automated test profiles, if you would. But since everything is defined on the screen, I'm going to go ahead and save the changes I've made just by hitting save. I already have a file name defined. We can see that here. DcPD for YouTube. When I click go to force, it's going to take me back to 200 pounds. And you'll be able to hear the fans spool up on the current source. I'm going to go to my DcPD screen. And I can see the DcPD status is warming up. My output current is 5 amps. This is the voltage loss at the current source. And this is my voltage as measured by the potential input. And what I want to do at this point is wait for any wiring or specimen to warm up. So I'm going to give it a little moment while it warms up. You can see my calculated K here, or crack stress intensity, of almost 3 KSI at 200 pounds. Once this number looks like it's stable, I will start the test and establish an initial crack length. Remember, we're in creep mode, so it's not going to do anything. There's not going to be any motion. It's just going to start taking DcPD readings. I'm going to go ahead and start the test and see if this is a good enough number for us to begin. So now what it's doing is it's building the crack voltage pool. It's going to grab its initial reading. And as you can see, since I'm running with such a small pool size, it already has. So now we have a live DcPD measured crack length of 0.4. And it's going to drift around. It may drift one way or another since I started this pretty quick. If there's any temperature change in the wires, since we're not running a reference, that will show up here. But for now, we're just going to let it log some data. I'm going to give it about 2 or 3 minutes to see what my initial crack length looks like before I start doing any motion. Now on the screen you can now see some lines have shown up after we've given it a few moments to log data. The purple line is my potential voltage, and the black line is my crack length. So the purple line is volts. You can see my voltage here on this scale, and my black line on this scale. And right now I'm just making sure I have a stable crack length reading. So maybe 5 minutes worth of data points, and then I can start to enter a fatigue motion profile, and we'll attempt to grow the crack. So now we can see I've paused the video and let some data accrue. I've got a couple more data points. Signal looks okay, considering the small amount of averaging I'm doing. Obviously, you could increase the level of averaging, but I wanted to keep this test very live, without a lot of averaging. Basically looking to see what my worst noise is. So now I'm going to go back to test profile, and I'm going to define a constant stress. I'm sorry, a sinusoidal K control. So I want my peak to be, for starters, 5 KSI. I'm going to start with a ratio of half and a frequency of 1 Hz. That should be adequate. Now, as soon as I save these new values, it's going to start that waveform. So let's do that. And we'll watch our live force screen. So here, you can see it starts off slow and gets to set point in terms of frequency. And it maintains 4,000, 4 KSI stress, and half of that. Remember, I'm operating in stress and not force, so the force is calculated. That means as crack length grows, the force can be shed so that you don't ductily fail your compact tension specimen. And if I look at my stress versus time, you can see it is going between my two set points for the K. Forgive me if I say stress when I mean to say K. Now, to show a sinusoidal waveform that's obviously moving much faster than I'm acquiring data, on the recorded data graphs, I alternate between the peak and the valley. And if I wait a few more moments here, I should acquire another data point. And the next data point should be right up here around 340 again. Or on the stress versus strain graph, stress versus time graph, 5,000 K, which is what I entered. There we go. So it's going to alternate to show that this is indeed a fatigue waveform. The smaller your sample rate, or the faster you sample, the closer these will be together. That does not indicate frequency at which the test was run. Let's take a look at our crack length and see what's going on. So we still look to be pretty stable now that we've started incrementing here. We're incrementing at a very low force on the specimen. So no cracking will occur. Basically, I'm checking my insulators. Some tests I've noticed, if the insulators aren't very good or you haven't installed the specimen properly, as soon as you start your fatigue test, your voltage will vary wildly. This can be an indication of loss of isolation electrically at the specimen. The specimen could be hitting a grip, or your insulator may have broken down. I'll let this run a little bit longer, and then I'm going to raise the peak stress, probably to 15K, so that I can start to mechanically grow crack. I'm pretty happy with my stability at even this low of a sample, or even low of an average pool. I'm not moving around a lot. If I wanted to stabilize the lines even more, I could, but I want to see that crack initiation. And to stabilize this even more, you'd simply add or increase the nanovolt pool size and the crack pool size. But like I said, I want to keep these low. I want to see crack initialization. So I'm going to stay in sinusoidal K control, and I'm going to take the peak K and bump it up to 10 and see if I have any crack initiation. So I'm going to hit save, go back to my graphs, look at my live force. And I notice my my upper is a little high. I'm going to increase the ratio to 0.8. Let's save that. Whoops, I went the wrong way. I'm sorry. 0.2. There we go. Perhaps my mistake is a good way to demonstrate how you can change the position of the waveform. And it'll come back up to speed here in a moment. There we go. And you can see the cycles over time and the frequency. Obviously this graph hasn't updated yet. Let's let it update. Once again, these graphs update every 30 seconds plus the sample rate. So with a sample rate of 30 seconds, it takes a minute for the graph to update. Okay, there's our update. You can see us changing frequencies here. Or, sorry, changing the K. Let's look at DcPD and see if we made a difference. See if we have any crack initiation whatsoever. I'm going to go ahead and pause the video again and start it in a moment after if I see some crack initiation. If not, I'll bump the stress up another 5 KSI. So picking back up, you can see my crack length hasn't really done anything. It's just hovering around its initial length. So I'm going to increase the stress to 15 KSI. Whoops, hang on. I had a brain shut down on me for a second. So 15 KSI. And we'll save that. And if you hear a big snap, that means you didn't do it correctly. back to the graphs and verify. No big snaps, that's good. Back to my DcPD graph. I'm noticing a trend here. The more stress I put on it, the more it falls. This could be insulation. Changing resistance just by how much force has been put on it. I'm going to pause the video and monitor that. And since I'm not showing any signs of crack initiation, I'm going to increase the stress value or K value another increment here to 20 KSI root mean square and save. If I check my graphs here, we can see increasing our force as we try and get the specimen to start a crack. Displacement. Stress for strain graph is not going to populate in this mode, but the stress for time graph will. Pressure is holding. Temperature 150 degrees Celsius the entire time. Frequencies at 1 Hz. Maintaining 1 Hz. DcPD. And after raising the K value, we can see crack initiation at this average size is very obvious once it starts. It takes a very sudden increase. And if we look at the force, you can see how I've been increasing it over time, and while the video has been paused, just to keep the video short. If I watch displacement, I'm making sure I'm not bending the specimen. It's one area where the LVDT is being installed during a DcPD test is useful. It lets you know if you're starting to bend or ductily fail the specimen. Stress versus time, like this is what I've been controlling is stress. I've gone from 10 to 15 to 20, and then the last few I've incremented slowly just to get that crack initiation. So that's definitely crack initiation. At this point, you could let the crack grow a little bit more to a set point. In fact, you could set the algorithms on the test profile screen. For instance, crack length is greater than 0.41. You could change it to a constant force of whatever you enter in this box here. You could change it to a creep test, and wherever it stops, it stops. Or even automatically pilot some other tests. Change it to a slow strain rate test. Or even change it to a stress per second test. Or delta K over delta time. For now, though, because at this point, there's many different tests you could run now that you've started the crack. But that just about wraps this video up in terms of pre-cracking a specimen in a Cortest load frame. Thanks for watching.